good to start with. So one of them is PN, the path on inverted. You look at a path, tell me the minimal number of colors that you would need for a proper coloring. And then we could also investigate the cycle. I don't like to start with the cycle on anything smaller than 3 because it's kind of topological. So you could do paths as your initial exploration case. You could do cycles as your initial exploration case. Or you could do the complete graphs, which coincides with the cycles for 3 vertices, but then quickly becomes different because this is something where all possible edges exist. If n is even, every vertex is adjacent to every other vertex. So if you try to make any pair of vertices be the same color, you have a problem. Every vertex does need its own color. What's your strategy for coloring?
Alternate every other.
Alternate the colors. So then, because you had already finished this, I asked you for a challenge graph where the chromatic number was 2.
We have found that every star graph.
So a star has one vertex that's adjacent to every other vertex, and these vertices are only adjacent. So you have like the center be A and then all the others are B. This is called a star. Okay, so you're gonna take your star, which is your starting point, and kind of alternate out. So these graphs that have the chromatic number equal to 2, the chromatic number are called bipartite. And the reason they're called bipartite is you can make you can take the vertex set and you can partition it into 2 sets so that the only edges occur between the 2 sets. So the vertex set can be separated into 2 disjoint subsets. I'm going to call A and B, but you could call them whatever you want, such that the only edges that occur are between a vertex in A and a vertex in B. You don't have any vertices you don't have any edges between vertices in A. Some people choose to do this kind of differently pedagogically, which is they give you this definition for bipartite, and then they kind of hit you with the chi of G equals 2, and then you show that they're equivalent. But if you think about it, if you have chi of G equals 2, you can take your 2 colors. You can make one color be one subset and one color be the other subset. And then for it to be a proper coloring, you cannot have things that are different colors, the same color be adjacent to each other. So this is what's called a bipartite graph. These are incredibly useful when you're modeling something where you have 2 types of things. So as an example, you might have donors and grants. The donors give to projects they believe in, and the grants receive money. But you can't have donors give to donors, and you can't have grants give to grants. Donors and grants are distinct classes. Another example would be you could have students be one of your unquote colors, and you could have the classes that they are taking be another. So this is a very special structure where you can draw it with the students on one side and the classes on the other, and then you can look for the relationships that exist here. 2 students are in the same class, blah, blah, blah. That's why this is worth considering, because it has this particular application when your vertices are 2 different types that don't. There's a special type of bipartite graphs that people always get mixed up. And so I'm going to try to do my best in this 1 minute to really burn this into your brain. Complete is different than complete bipartite. You remember that complete is different than complete bipartite. Have different notation. The complete graph is K sub n, which means it has n vertices and all possible pairs of edges. Then you have complete bipartite. Complete bipartite has 2 numbers. It has m and n. You have m vertices of one type and n vertices of another, and all possible edges between the 2 types, but not all possible edges that could exist, because you don't have edges between vertices of the same type. Yes, every A is adjacent to every B, and every B is adjacent to every A. But as an example, this would be a diagram for K23. I have 2 vertices in one part. I have 3 vertices in the other part. I have all possible edges between them. But I don't have any vertices or edges between the A, and I don't have any edges between them. Whereas if I have K5, five was a bad choice, but I have all possible edges, and there's no notion of having two separate parts. It's all possible connections. Did I get all of them? There should be 10 because 5 choose 2. Whereas how many vertices are going to be here? For Kn, there are n choose 2 edges. How many will there be for the complete bipartite graph Kmn? So I won't see you in person on Friday. I will have something up for you to work on.